Hello, everyone. My name is Jack Beardshear. I'm a grad student in the LACE group here at UT. My presentation is on dilute magnetic semiconductors, in particular for optoelectronic applications. So we'll get started with an introduction to dilute magnetic semiconductors. What they are is very simple. You start with a normal semiconductor material, and you introduce into it these magnetic dopants here. Typically, when we're selecting a magnetic dopant, we go with one of the 3D block metals, so the magnetic metals, and by far the most widely selected of which is manganese, primarily because if you follow Hund's rule, you'd find that it has 5 electrons in the D shell, which allows it to contribute significantly to the magnetism of the material. And in particular, a lot of different material systems have been studied. So we have some 2,6 semiconductors like cadmium telluride, as well as some 3,5 semiconductors like gallium arsenide. And by far the most widely studied of which is gallium manganese arsenide because it tends to have a lot of favorable properties, which we'll get into later. And for the most part, these materials are grown using low temperature molecular beam epitaxy, which is a non-equilibrium growth technique, and it helps you incorporate more of the magnetic dopants into the semiconductor material. So some basic properties of the materials. Number one is that it's ferromagnetic, which means that it has an associated Curie temperature below which it can exhibit magnetism, or ferromagnetism. And if you take a look at the 3,5 materials, you'll see that most of them have very low Curie temperature. And the highest of which is gallium arsenide. Gallium arsenide tends to max out at around 170 to 180 Kelvin in its Curie temperature. So for the most part, we're limited to operating our devices near like liquid nitrogen, for example, at 77 Kelvin. And they have typically a saturation magnetization that's in the range of 10 to 100 times lower than typical ferromagnetic metal. And what really makes DMS materials stand out from other materials is that their ferromagnetism is carrier mediated by holes in the valence band. And so what you can do is if you plot the Curie temperature versus the hole density, what you'd find is that it actually scales like the hole density to the 1/3 power. And really why this happens is because manganese in the 3,5 materials acts as a shallow level acceptor. So when you dope it, it actually becomes p-type. And so really trying to understand why these materials are ferromagnetic is actually very difficult. And I've kind of highlighted here that the mechanism is still something that's under debate. I would consider it something of an open question. However, this kind of leading theory that I've picked out here is the PD-Zener model. And how the PD-Zener model works is you have these localized magnetic dopants and you have these delocalized holes, and they interact via like a RKKY coupling. And so typically the PD-Zener model is like a mean field theory RKKY like exchange coupling interaction. And that allows for ferromagnetic alignment of the carriers. I should also mention that there are a lot of other proposed mechanisms for explaining this kind of behavior, like double exchange carrier hopping, bound magnetic polarons, as well as just unrelated defects. So it is really kind of something that's under debate. But I think the PD-Zener model is kind of the best model that we have at explaining the properties. So getting into why it's interesting for optoelectronics, DMS materials have some very interesting magneto-optical properties, which are very unique. The first is that its electroluminescence is spin polarized. And so where this comes from is what's known as the optical selection rules. Essentially, when you have an optical transition, you have to conserve the total angular momentum. And so what that means is that the quantum number mj must increase or decrease by 1, depending on whether you're absorbing or emitting a right or left circularly polarized photon. And what that means is that certain spin states can only absorb or emit into other certain spin states. So if you have a spin polarized carrier density, then you end up preferentially emitting or absorbing into either right or left polarized photons. The second property is giant Zeeman splitting, and this is fairly straightforward. It's just a splitting of the band edges for up and down spin states. But really, the interesting thing that this leads to is what's known as magnetic circular dichroism. And where this comes from is because the joint density of states between the up and down transitions are actually different because of the giant Zeeman splitting. You end up with a difference in the absorption coefficient for right and left circularly polarized photons. So one unique device that makes use of these interesting properties is the spin LED. And what the spin LED is it's an LED that is polarized emission. And the way it works is you have a DMS, so in this case gallium manganese arsenide spin aligning layer, which is polarized in plane. And you apply bias to inject a spin current into this indium gallium arsenide quantum well active region. And the electron hole pairs are spin polarized, and so their emission, when they recombine, is also polarized. And what you can see here on the right, if you take a look at the hysteresis for this device, you can switch the magnetization of the DMS layer just by applying an external magnetic field, and what you'll find is that the polarization switches depending on what applied field you're adding. And so what this means is that you can design an LED that has the ability to flip between emitting right and left polarized photons, which is very cool. A second device I'd like to highlight, another optoelectronic device, is the spin photodiode. And the spin photodiode works very similar to the spin LED, but in reverse. So instead of emitting, it's absorbing a circularly polarized beam of photons. And how it works is you start with a p-type gallium manganese arsenide layer here on the left, and on the right you have your normal n-type gallium arsenide. And so when you join them, it becomes a p-n junction. So the typical setup for a optoelectronic photodiode. When you apply a circularly polarized beam of photons illuminating the device, you generate a spin polarized carrier density, and those carriers get collected with different efficiencies depending on the magnetization state of your DMS layer. And so what will happen is that the spins tend to accumulate in this n-type gallium arsenide layer depending on whether or not you're absorbing the right or left polarized photon. And if you kind of squint and turn your head sideways, what you'll find is that this structure looks almost like a magnetic tunnel junction, with the barrier being the p-n junction. And it's not surprising from there that if you take a look at the hysteresis of this structure, you'd find something that also looks like that of a magnetic tunnel junction, where actually your hysteresis is with the open circuit voltage of the device. And so you can essentially use this device to analyze whether or not your incoming light is right or left circularly polarized. So moving on to kind of discussing the advantages and limitations of the material systems. The primary advantage of using DMS materials is that it's very easy to integrate with existing optoelectronic devices, particularly the 3.5s, which kind of tend to be one of the dominant platforms for optoelectronics. And they have really excellent tunability because you can alloy the 3.5s. For example, you could add indium to your gallium manganese arsenide to tune your emission wavelength and your band edges and other sorts of properties. And you could also switch these devices. As I mentioned, you can apply an external field or even a spin current to try and switch the magnetization state of your device. But really, the limitations of the material are pretty glaring. The first of which is the low Curie temperature. As of right now, no devices can operate at 300 Kelvin because the Curie temperature is just too low. And in addition to that, a kind of related issue is just general material quality. You can only really incorporate up to about 11% at highest in into gallium arsenide. And if you try and push the manganese incorporation higher, you introduce a lot of defects and disorder into your material, and that tends to accelerate spin relaxation. And so, yeah, moving on to the conclusions. I would say that DMS materials are a very interesting proof of concept at current moment, but they're very limited in their applications. But there are a lot of future directions. For one, gallium manganese arsenide could potentially get pushed to a higher Curie temperature through improved growth and processing, which I could get into. And then additionally, we could improve our understanding of the mechanism for ferromagnetism, which, as I mentioned, is somewhat of an open question, and that could help us push to higher temperatures as well. And we could even explore things like band engineering with different alloys, and you could even push the impurity band level relative to the band edges around potentially. And there's a lot of interesting applications in the future that could become relevant. For example, you could have a integrated photonics and spintronics platform, all of which is kind of on chip. So with that, yeah, I'll thank you all. And if there are any questions.